I mentioned it kind of briefly when we were going through naming the individual ions, but here we're going to get into some more practice writing ionic formulas as well as how to name them. They here use the example of iodized salt having potassium iodide, which is Ki, in there, and of course the salt itself is sodium chloride, which we've used as an example plenty of time. So when it comes to naming an ionic compound, the metal, we just write its name. Its name doesn't change. When it comes to the nonmetal, it says here it's the first syllable, and that's not quite correct. Frequently it is, but it's just something you kind of got to get used to. Honestly, you'll hear these names often enough, and like I said, I'm not going to penalize you if you drop too much or too little, and any spell checker, if you're answering homework questions online, any spell checker is going to catch that you spelled a word wrong if you go to turn oxygen into oxide instead of oxide. It's going to fix it for you. But for example, nitrogen becoming nitride, phosphorus becoming phosphide, that's more than one syllable that's being kept. But anyway, we keep the beginning of the element name and we replace the ending with "ide." And then there's always a space between the two parts of the name, and so we don't smush the two element names together. So potassium iodide was there on the first one, and as I mentioned back when we are doing ions, we have the potassium ion and the iodide ion. When they come together, those charges end up canceling out anyway, and so because those charges cancel out, then we just drop the word ion from it and call it potassium iodide. And just be careful the suffix change there on the nonmetal, or more specifically on the anion. One thing I will point out, and it throws everyone, is the numbers do not enter the name. And so even though this is Al2O3, over here we just have aluminum oxide. And you're probably thinking to yourself, wait a second, I know of something like carbon dioxide, and that di means 2. The number is in the name. Well, that's a different naming system. This one for ionic naming is actually called the stock naming system. And the covalently bonded things, they use something called the prefix naming system, which does use numeric prefixes. The reason it becomes necessary there is because you can't figure out the formula without that. When we have the charges, as we were looking at previously, you can just do the crisscross thing. You bring that 2 down here on the bromine, you bring the invisible 1 on bromine down here to the magnesium, and you end up with MgBr2. You don't need the numbers to be given to you because you can figure it out from the charges. Would it be simpler if the numbers are in the name? Probably so. Unfortunately, that's just not the rules in chemistry, and it's just something you got to get used to. So on this one here, we're just asked to name it. So we named the metal potassium. And then we identify the nonmetal. It's oxygen, and we're going to drop that suffix and replace it with "ide." More practice over here. We have calcium oxide, aluminum sulfide, and the last one here is magnesium chloride. IDE suffix on all of those. This one here asks us to write the formulas and to come up with the names. I'll do the best I can to keep it legible here, but I'm doing the crisscross thing. I'm just doing it in my head. I don't know of many students who start out doing that, but we have NABR, Na2S, and Na3N. On this one here, we're going to have AlBr3, Al2S3, and this one here we have Al. You might be thinking to yourself, wait a second, I did the crisscross thing and I have 3 and 3. This is one that would reduce. The other one that would reduce here is this one because they have the same charges, but since they're both invisible 1s, they can't reduce anymore. For naming, these all start out sodium in this row. Sodium, and we have bromide, sodium sulfide, and sodium nitride. Down here, they all start with aluminum, bromide, and the second word is the same as it was up above. So aluminum sulfide, and lastly, aluminum nitride. So we've talked about how everything in the first two columns have the same charge, and things over on the right-hand side, for the most part, have the same charge, and it's based off their column. We skipped the transition metals on purpose. Well, with the transition metals, most of them can form two or more charges, two or more positively charged pieces. Manganese, I believe, is the one that has the most, and it takes on 7 different charges, one of which is a 8+ charge, and I believe there's even a negative version in there as well. And there's a few small exceptions, zinc, cadmium, and silver. If you want to get into the other metals, poor metals, the things leading up to the metalloids, aluminum is also an exception. It's always a 3+ charge. Everything else in that region, lead and tin and bismuth and so on, they can all take on multiple charges. Because of that, they need a number in their name. And what we've chosen to do for those numbers is to use Roman numerals. And so we have the copper 2, copper 1, iron 2, iron 3. Now, this is much better than an older system. In that older system, there was cuprous and cupric, where one of them was the lower charge and the other one was the higher charge. And so here we had ferrous and ferric. And the awkward thing is here cuprous is a 1+, but here it was 2+. Here the ic suffix is a 2+, but here it was a 3+. It just was annoying because you really had to just memorize extra things. The Roman numeral system was developed instead, and so this is how we'll go about naming them. I will say occasionally you'll still hear these old ones, and with those old ones, it allows me to bring up the lame chemist joke that when you have a whole bunch of Fe2+ ions in a circle, it's a Ferris wheel. The Roman numerals here tell us the charge. The awkward thing is frequently, because we do the crisscross thing, that is going to end up as the subscript on the other piece. But it is not the subscript on the metal, it is the charge on the metal, or more specifically, the cation, that gives us the Roman numeral. And in case you don't know your Roman numerals, 1 is I, 2 is II, 3 is III, 4 is IV, and essentially up to that point we're saying it's this many I's. At this point we're saying it's 1 less than 5. And if you have a smaller number in front of a bigger number, then it's that. Frequently you'll see the serifs, the bars over them, drawn over the whole thing, which is why I've done that there on the V. But 5 is V, 6 is VI, 7 is VII, and 8 is VIII. And we're not going to need higher than that. Heck, we'll generally not need higher than 4 because of the octet rule. That once you get to having this many valence electrons, it's easier to gain than it is to lose electrons. And so it's going to tend to be just the first 4 Roman numerals. But just in case you don't know them, they're there. And here are some examples. Feel free to pause it if you want. I will point out here that Mercury 2 is a weird situation, and you should take a moment and read that. It comes up rarely. So this one here walks through how do you figure out the charge if you're not given to it. Obviously, if you're given it in a name like iron 2 chloride, well, then you know you have the iron with the 2+ charge and the chloride with the 1- charge, and you do the crisscross thing, you end up with FeCl2, and you can come up with the formula from there. The chloride is charge you could look up. The iron 2 you are given is charged from over here. The reverse process is similar. You can almost do a reverse crisscross thing. There's times where it doesn't work, though, because of that reducing that can happen. So it's always easier just to figure out what the total negative charge is and therefore what the positive charge must be. So fluoride has a 1- charge. I went ahead and drew the 1 this time, which means we have a total of 2-, which means to end up with 0 for our total charge, then the total over here has to be 2+. Well, if that one's 2+, and then I have only one of them, then that 1 must be a 2+ charge. And so then we have manganese 2 fluoride. And I will point out as well, when we do the Roman numerals, there's not a space there. I was taught that wrong, typed it wrong for years, and now I know, and I follow the correct rules. We mentioned already charges, and previously we saw the kind of a partial periodic table that had the charges on either side, although I think they left these off back there. But I will point out that all of these that they've left off are just ones we won't use commonly, but they also happen to have variable charges. If it's not a metal in the first two columns, or one of those few exceptions, silver, cadmium, zinc, and aluminum, and I will point out that they're all kind of clustered right over here in the same region. There's a reason for that. You don't need to worry about why. If it's not those, and it's not the ones over here at the beginning, then there's going to be variable charges. And because there's variable charges, then a Roman numeral has to enter the name. I actually just did this one accidentally as a moment ago. I promise I hadn't looked ahead and didn't actually know this one was coming up. But we need to name this thing. When I'm naming one with the transition metal, I always like to go ahead and just get what I know out of the way. And so I know that's iron something chloride, and that something's going to be a Roman numeral. I know that because it's in the middle of the periodic table. It's going to have a Roman numeral. So from there, we know that the chloride is 1 minus, so that gives us a total negative charge of 2 minus. For that to equal 0, we must have a positive charge of 2 plus here. Since there's only one of them, then the iron has to be a 2 plus, and so Roman numeral 2 goes there. This next one here is an example where trying to do the reverse crisscross thing wouldn't work because this one reduced. I'll work it out the way I just did the prior one, then I'll show you what I mean by reducing and how reverse crisscross doesn't work. What we have here is manganese, and then Roman numeral is going to go inside the parentheses there, and then oxide. So we've done those already. Now we need to factor in the charges. Well, oxygen here has a 2 minus charge. There's 2 of them, and so that gives us a total of 4 minus. Manganese then must have a 4 plus, so that the sum of those two is 0. Since there's only one of them, then that one manganese must have a total of 4 for its charge, so IV in there. If instead you'd been given the name manganese 4 oxide, then you would have done this. You do the crisscross thing. Remember, we just bring down the number and not the sign there. I accidentally circled the sign. And you'd end up with Mn2O4, which then can reduce or simplify down to MnO2. And so this makes it so that you can't just do a reverse crisscross thing as you might be led to believe, that you could just take this one and bring it up here and say, oh, that's its charge. Because when you do it that way, this charge has to, the subscript on the metal has to match the charge on the nonmetal. If it doesn't, because when you bring this invisible 1, you'd have invisible 1 here, but oxygen, it turns out, is actually a negative 2. Well, then with 2 of them, that means this one has to be a 4 plus and not just the 2 that a reverse crisscross would lead you to do. So crisscross trick is great for going from a name to a formula. It doesn't work so much going from a formula to a name when you have these charges involved. You really kind of have to just do the math here. Not that it's hard math. I will point out that all the examples we've done so far here, we have only had one metal. That is super common. However, there are some situations where you have more than one metal. Fe2O3, for example. And so I want to show what this one looks like. Cut out changing the pen color when you have more than one metal there. So like I said, this one here is iron oxide, and then we're going to need a Roman numeral there still. Oxygen has a 2 minus charge, which gives us a total negative charge of 6 minus, and that means the total positive charge here has to be 6 plus, but that's the total. Since there's 2 of them, then each one of them must have a 3 plus charge, and so Roman numeral 3 here for this one. And just to emphasize why this is important, it's because iron can have more than one charge. When iron has a different charge, there is such a thing as iron 2 oxide. And if you do that one, Fe2 plus, O2 minus, do the crisscross thing, you end up with Fe2O2, simplifies down to FeO. And so we have 2 things that would be named iron oxide, Fe2O3 and FeO, and so we have to have a different name for them, and it's because the metal has a different charge as to why they have different formulas, and so then we use Roman numerals to distinguish those 2 from one another. This slide just says more of the same, so I'm just going to move right along. And here we're going to come up with the formula for 10,2 chloride. So that's SN with the 2 plus charge, Cl with the 1 minus charge, and that gives us SnCl2. Some more practice over here. Nickel 2 sulfide, so that's Ni2 plus S2 minus. Do the crisscross thing, you end up with Ni2S2, which simplifies down to NiS. Zinc chloride, notice they didn't give us a charge here, and that's because zinc is one of those few that doesn't need a Roman numeral. So zinc is always a 2 plus charge. Unfortunately, that's just something that you're going to have to know for the zinc, silver, cadmium, and aluminum, although feel free to have them on your note card. Anyway, ZnCl2 then is how that one comes out to be, and I just actually worked that one out a moment ago as well, and they actually had it on their chart there just a moment ago, but it never hurts to practice it again. So iron 3 oxide, Fe3 plus O2 minus, do the crisscross thing, and you end up with Fe2O3. And that finishes up section 3.